It looks like we can start. Pretty small class today, but we'll do the best we can. We're just about ready to close out week 7. And so the announcements of the day are that quiz 5 is due today. The new quiz is number 6 posted. And we're going to be working through section 6.5 on solving polynomial equations, and then making the jump into chapter 7, dealing with the rational functions. So that's a plan so far for today. We've covered a lot of ground on this particular week, but section 7.1 is pretty short. 6.4 was a review section on factoring. And what we'll find out pretty soon in section 6.5 is it's just really more factoring. So it's kind of nice in a way that after beginning factoring in section 6.1, 6.2, really we're going to be using that as a skill quite a bit throughout the course. But any questions at all, folks, before we get started today? Okay, and maybe just another reminder. On Friday, tomorrow, probably early in the morning before even the grading, I'll be working on putting down the information for exam 2, saying what the exact sections are for this exam, and posting exam review materials as well. So this should show up on Friday, probably before 1 o'clock, I would say at the latest, if you want to get an early start on studying those topics. So we're in section 6.5, and here's how it starts out. So we're going to start dealing with the so-called quadratic equations. What makes an equation quadratic, that's kind of an interesting word, is the fact that there's a power of 2 inside the equation. So there'll be things like ax squared plus bx plus c equals 0. A, b, and c can be any real number, with the requirement that a is not 0, because if a was 0, the degree 2 term would disappear, and it's just bx plus c, making it a linear equation. So another way to say it is a quadratic equation is a degree 2 coming from the highest power that appears in that equation. Well, that's the equations we're going to be solving. And the fundamental idea that makes all of this work is the so-called zero product rule, or zero product property, it's sometimes called. This is a property of just ordinary real numbers that we deal with every day. And the thought is, it's impossible to have one number multiplying another number, resulting in 0 without the first or the second one being 0 in the first place. 5 times 3 gives us 15. A times b, resulting in 0, means either a was 0 or b was 0. So it doesn't seem like a big statement, but this is the major reason why we wanted factoring. If we can factor something into something times something equals 0, it allows us to split into 2 different equations, and then we can solve both of them. Well, any questions at all, folks, with the ideas so far before we go to try it out? Okay, part A is kind of like a warm-up. Notice it's not even in a quadratic equation at all. There's no x power term at all inside of this. But really, the zero product property still applies here. If we have 3 times x equals 0, then either it implies the first thing is 0, 3, that's impossible, 3 is not 0, or the second thing is 0. So by the zero product rule, x would be immediately 0 on this one as well. Sure, the ordinary algebraic steps would just be to divide by 3 on both sides, and you get the same result. But it's interesting to show that this rule is actually working out for us as well on this problem here. There's another case where it would work out really nicely. This one is a quadratic equation, because if we were to FOIL this out, we would get a 3x squared. So there'd be an x power 2 term. But actually, multiplying this out does not help us solve this equation at all. In its factored form, just like this, it's ready to solve. So the zero product rule, let me read you how I highlighted that. The idea is it says if you have a first number multiplied by a second number, or algebraic expression multiplying algebraic expression, and if it's set equal to 0, if all those things align, then you can either say the first thing is equal to 0, or the second thing is equal to 0. And that's exactly what we have over here. X plus 5 times 3x minus 9 equaling 0 means either x plus 5 is 0, or 3x minus 9 is 0. So this equation was really kind of nice in a way. In its fully factored form, the solutions are just being revealed to us. This is now two linear equations because the degree is 1 on both these expressions. We can solve them both really rapidly. On this one, subtract 5. X would be negative 5. On the second one, add 9. Divide by 3. And x would be 3. So those are our two solutions here and here. If we want to write them in on one line, we might write it x equals negative 5, comma 3, just as a summary. Well, we did it, folks. That's our first quadratic equation we've solved. Any questions at all solving this one? Okay, well, we should definitely practice several more. This one was nice because it came pre-factored for us. It was also ready to go in the zero product rule because 0 was on one side. And essentially, these are the steps we need to take on each of the next problems. When it gets all scrambled up, if someone expanded this using the FOIL method and add terms to both sides, now it's a harder equation. So step 1 would have been, let me spell that right first. Step 1 is to get 0 on one side. Which makes sense because if there's a zero product rule that we're using to solve these, it doesn't apply unless there is specifically a 0 in the problem. Then step 2, factor completely. Or we could just say briefly, factor it. That's what we had here that was helping us out. We added it in a nice factored form. Then step 3, set factors equal to 0 and solve. Setting the factors equals to 0 is just this part right here, the a equals 0 or the b equals 0. So we'll try that out on the next problem. And here's how it goes. 3y squared equals negative 24y. This one's not as nice as part B. And notice one thing we can't do on this one is divide by y. If we divide by y in that equation, we can get something to solve, but we're not going to get all of the solutions to this one. So if we want to find all solutions, and there's multiple because degree 2 often implies 2 solutions, but not always. We'll see exceptions to that. Very first step we have to do is get 0 on one side. So add 24y to both sides of the equation. We now have 3y squared plus 24y equals 0. Next step is we just factor the equation as we see it. This one comes in with 2 terms, but 3 divides 24, so that says there's a greatest common factor we should pull out. And also y divides both terms because y appears in both. So if we factor this, it really just amounts to factoring out the greatest common factor. 3y divide here is just going to leave us with a y. 3y divided by this term leaves us with just an 8. So we get 3y times y plus 8 equals 0, and we have everything aligned. It's pretty much the same problem as before, except that the first factor is just 3y rather than something like an x plus 5. But still works out the same way. Either this is 0 or this is 0. Let me put it on the next page so we can not squeeze it in. Setting this one to 0, that's actually the first problem that we looked at in the notes. That was when we were solving 3x equals 0. Just a different variable, 3y is 0 now. Set this to 0, we have y plus 8 set to 0. I like to put the or in the middle just to say now there's 2 possibilities. Either the solution we get from here or here. Now you can look just by visual inspection. Throw a 0 in there, it's 3 times 0, the equation balances. So y equals 0 is one solution. And I like to write in the step just because it reminds me of the process. But even up here, you can kind of see the solution as well. Put a negative 8 right where the red dot is. Then this entire group is 0 times negative 24. and it balances to 0. So just by visual inspection, right, at this stage, we can see the solution. The solutions to 3y squared equals negative 24y are 0, negative 8. We did it, folks. That's a trickier one because we had to use all the steps, getting 0 on one side, then factoring. Then at this step, it's the zero product property. Any questions at all getting through this one? Okay, this is a good point to kind of pause and reflect on how the algebra works with this kind of thing. If we had something that looked like, say, 3y equals negative 24, this is no big deal. We don't need to factor this at all. We just divide by 3 on both sides. We get y equals negative 8, and then we're done. That's why these kind of equations really represent a pretty big fundamental change, because now if it's 3y squared equals negative 24y, this is where it does go wrong. So let's make that seem like an incorrect step. Dividing by y does not give all solutions. So let's try it out just to see that. If I divide by y here and here, that's something that we might try, because if y is not 0, that's a bona fide algebraic step. And you would get 3y on the left equals negative 24 on the right. Then you could divide by 3 again and get y equals negative 8. But we know that this is not the total set of solutions. There are 2 of them, y equals 0 and y equals negative 8. So dividing by y on this one just doesn't help us out at all. So watch out for that in the homework as well. If we come up with one solution that's not good enough, the whole problem would be marked as incorrect, and we would have to try again. So the total solution set are both of those numbers, 0 and negative 8. We'll try it out again on the next problem, see how it goes. And notice how kind of disheartening the next problem is. If that was a 0 right here by the red dot, we can already tell what the answers are. It would have been positive 5, negative 3. But the fact that that's a 9 means we actually have a lot of work to do on this one. In other words, the factoring that happened right here is of no value to us whatsoever if there's a non-zero number on the right-hand side. So that setting equal to 0 is the critical part of this entire idea, this entire method for equation solving. So first thing we'll do is undo this factorization. Let's expand out the left-hand side. Multiplying x by x will give us x squared. X by positive 3 is plus 3x. Distribute the negative 5 through, so now it's a negative 5x. Here to here will be minus 15. And the whole thing is set equal to a 9. Now, combine like terms. We have x squared minus 2x minus 15 equals 9. And we're about at this stage now where we're going to get 0 on one side. Subtract 9 from both sides, and now it's an x squared minus 2x minus 24 equals 0. That's progress. So now we have 0 on one side. On the other hand, though, this is still unfactored, so we have to do a little bit more work on the left-hand side. On the prior problem, it was just factoring out the greatest common factor. 2 terms, not being a difference of squares or a sum of cubes or a difference of cubes, means that's pretty much our go-to method, greatest common factor. But this one's 3 terms, so that suggests it ought to factor in a different kind of way. Let's go 2 sets of parentheses, both multiplying resulting in 0. This is now factoring just using the trial and error method. For x squared, we would have an x times x. For the negative 24 here, well, first, because it's a negative sign, our signs have to be mixed, so plus and minus. Then good choices with the negative 24 could be 8 times 3, hard to see how to get an 8 times 3 to come out as a -2. But we've also got a 6 times 4 that we can work with. If we go a -6 and a +4, then we don't have to FOIL out the whole thing because, for example, we already know x times x is x squared. That's why we put the x's there. We already know that 4 times -6 is the -24. Again, that's why we're using those specific numbers, 4 and 6, with a plus and minus. What we wonder is if we get the -2x. So this is really just doing the same kind of check we've been doing all along since section 6.2. Multiply here to here, and that's a -6x. Here to here, that's a +4x. Add those together, we get -2x. That does land on the middle term, -2x. So the factorization is complete right at that step. But it's not over. You never want to celebrate too early with these kind of problems because remember, on the prior sections, there was no equality. It was just some kind of expression that looked like this, and we were factoring it. This time it's an equation. We have to come up with solutions for x, so now it's a really pretty different kind of problem. But now it's just the zero product property once again. We have one factor multiplying another factor. This directly and immediately implies x plus 4 is 0, or x minus 6 is 0. These are immediately solved just by, on this one, subtracting 4 from both sides. On this one, add 6 from both sides. And those are the two solutions to this original equation way up top. Well, we did it, folks. That's the whole rundown for solving this one. Any questions at all running from the start to end on this one here? Okay. If you were doing this problem and you had the extra time, these aren't too hard to check. Sometimes with some of the algebra we do, the check is just about as hard as the work itself or even harder. So when you have an easy check available to you, might as well give it a try. If you plug -4 back up here, this is the check. When x is -4, the equation right by the red dot turns into -4 minus 5, -4 plus 3 equals 9. So this is going to turn into -9. Multiplying a -1 equals +9, and that's true. This is just the property a negative times a negative, resulting in a positive. So -4 works. Then if we check x equals +6, go back to the drawing board over here in the original equation, we'll have 6 minus 5, 6 plus 3 equals 9. This is just 1 times 9. So x equals 6 also checks out. So it's just a really fast arithmetic to see if we have the right values. Trying to guess a -4 and +6 just based off these numbers, that would have taken me all day. So this is definitely the best approach. And the factoring and the equations gets harder as we go. So even though you might have been able to guess the right numbers, it doesn't get any easier. These are kind of the warm-up problems for the equations. We have a couple tougher ones that we're going to give a try next. And these ones come in as actual bona fide word problems. So let's give these a try. We'll work them out carefully to see how they go. These are the last two problems of the section. Well, this says the length of the longer leg of a right triangle is 13 meters more than 3 times the length of the shorter leg. They told us a lot of information right there. First of all, there's a right triangle. Apparently one of the legs is really long relative to the other. So I'm going to draw something about that like that. Here's my right triangle with a really long leg relative to the other leg. When it says the leg of a right triangle, we're referring to this side and this side. The longest side is what we would refer to as the hypotenuse. And the drawing doesn't have to be perfect. I've noticed it's a little bent right over here, but that's okay. Let's leave it that way just to say you don't have to be an artist for this. Some people are pretty talented, but I'm not the best. The fact that it's a right angle means there's a 90-degree measurement right here. So you might put that in just to convey that information. And now let's see how this information relates. The length of the longer leg is 13 meters more. But here's the longer leg, so let's go 13 meters more plus 13. Then 3 times the length of the shorter leg. Because the shorter leg came last in the statement, it's a good idea to place the variable here. Then 3 times the length of the shorter leg would just be 3x. So we've related x as the shorter leg. The longer leg is now 13 meters more than 3 times x, 3 times the length of the shorter leg. So that takes care of this very first sentence. Any questions at all getting the x, 3x plus 13 so far? Okay, so again, when I thought of the shorter leg, I was thinking of the x right here. And now the next sentence says the length of the hypotenuse is 14 meters more than, again, 3 times the length of the shorter leg. So that's just x coming up again. Let's read through that again. Hypotenuse is 14 meters more. So I'll go plus 14. There, we've done that part. There's an increase by 14 meters, but it's more than 3 times the length of the shorter leg. That would just be 3x once again. So we've got the entire right triangle diagram set out. And now it seems weird, but it's actually a pretty good idea to add even more variables to this. Let's let A be the length of this shorter leg, B be the length of the longer leg. You could actually swap these. You could have put B over here and A over here. You would get the same result. But because we're about to write down Pythagorean's theorem, the only big rule about this is C, the other variable, should always be the hypotenuse, the longest length. Then, I think this is our second look at Pythagorean's theorem. Pythagorean's theorem says a squared plus b squared is equal to c squared. And this is where we're going to get a polynomial equation finally. We'll substitute the information into these 3 different places based off this right triangle diagram we built, and then solve that equation for x. It says find the side lengths of the triangle. I interpret that to mean we want the length of all 3 sides. Any questions before we start? Okay, let's give this a try then. So in place of a squared, let me put in just a parenthesis, raise it to power 2. We're just plugging in x itself. Not so bad. We can just drop these parentheses. I'm putting in parentheses just to be ultra careful, because over here where it says b squared, those parentheses are mandatory now. Without the parentheses, we have the wrong algebraic expression in place of b, and I don't think I made those long enough. Okay, here's b squared finally. In place of where b was, we're throwing in the 3x plus 13, so another substitution. And another substitution from over here where c was. It's to power 2, but in place of c, put 3x plus 14. Okay, so we've got an equation we can work out. I'm going to move it down over here just so we have enough horizontal space for this. First term is just going to be x squared plus this one, we need to actually FOIL out. This is really just the result of 3x plus 13 times 3x plus 13. So it's a perfect square polynomial. We're now undoing the factorization on this one. And same on the right-hand side. This is 3x plus 14 times 3x plus 14. Now, it's looking like a pretty big equation, but really we're going to apply the same ideas from before. We need to get 0 on one side, but before we even get to that step, we should expand both sides of the equation, combine all of our like terms, and then move everything over either to the left side or to the right side, whichever looks visually more convenient. So here's our next line, copy down x squared. Now we're foiling all of this out. 3x times 3x will be plus 9x squared. 3x times 13 is plus 39x. Rinse and repeat. 13 times 3x is 39x again. 13 times 13 is 169. And now the left-hand side is done. So do it all over again. It's slightly different because of the 14s. Starts off similar. 3x times 3x will be the 9x squared. 3x times 14 is going to be, let's see here, that'll be 30. 4 by 3 is 12. Looks like a 42x. Stretching the limitations of my mental arithmetic late at night for an evening class. This is the same multiplication, 42x again. Now, one of these days I'll memorize 14 times 14. Didn't happen today, but maybe one day I'll get there. For all the rest of the times you get larger numbers, don't forget, on the upcoming exam, you are allowed a calculator for these kind of situations. So that comes out as a 196. Really, this equation looks worse, the line we're on, because it got expanded by a lot. But this is an improvement. These factorizations are of no good to us until we get 0 on one side and we get a complete factorization. So at this stage, we might combine like terms, but notice there is kind of a nice thing that happened on this equation. If there's 9x squared on the left side, an exact copy 9x squared on the right-hand side, you can just subtract them from both sides of the equations right at this stage. So go minus 9x squared, minus 9x squared, and that's just gone from the problem. So this results in x squared. We have 39x plus 39x, so that's a plus 70, let me try again, 78x plus 169 equals, this 9x squared is gone, 42x is going to be 84x plus 196. So just about there. Our main objective was to get 0 on one side, and we've just about got it. Let's subtract 84x from both sides. Subtract 196 from both sides. Now our new polynomial equation is x squared minus 78 minus 84x's is going to give us negative 6x. And let's be really careful with this one. 169 minus 196, giving us a negative 27 on this column, is now set equal to 0. So quite a lot of algebra on this one. This one's kind of a good tour of lots of different things algebraically. Finally, at this stage, we have a quadratic equation, degree 2. It's set equal to 0. So if we can factor this, we're home free. We'll be able to say what the lengths are of this original right triangle. So let's start factoring this thing. X squared we can split up as x times x. For a negative here, that suggests a plus and a minus. And if we can figure out what goes in these last positions, we're home free. Anyone see any two good values that could work for these two? Oh, just saw the chat. Yeah, I think a 3 would be a great call on this one. So if we're using a 3, that means we're using both a 9 and a 3 to get the 27. So let's try out, I'll put 3 and 9. This is trial and error, so I don't know right away that this is going to work. I just drop them in that order. Multiply here to here as our part of our check, and that's going to be a negative 9x. Multiply here to here, that's positive 3x. This now adds up, combining the like terms, to a negative 6x. That means we nailed that term right there, negative 6x, and the factorization is complete. So yeah, absolutely. Good call on that one, Tracy. The 3 there did the job for us. Well, now that we're here, we're just about done. The zero product property is in effect. If something times something else is multiplying, and they are, that's why we love factoring, and if those multiplications are set equal to 0, the automatic implication is the first factor is 0 or the second factor is 0. They're both immediately solved for. Subtract 3 for both sides on this one. X is negative 3. Add 9 to both sides, or X is 9. Now we have to say, on the original part of the problem, find the lengths of the triangle. And thinking about that these are lengths of a triangle, one of our solution is a little bit weird. Ordinarily, we don't hate negative numbers as a solution, but negative 3 does not fit here. If we were building cabinets, or if we were building just some kind of actual structure, maybe in someone's backyard, and we try to order negative 3 meters of wood to do this part right here, we're probably going to be fired on the spot right there. And same in this situation. We have to throw away negative 3 since X is a length. X is not equal to negative 3. So we just toss that one out. It's gone. The side lengths then are X equals 9 meters. We'll plug 9 meters here. Let's maybe say this in a way that kind of relates the whole problem. The shorter side, that's this way, has side length X, which came out at 9 meters. The longer side, that one was 3 times X plus 13, but we're throwing a 9 inside of there. That's a good one for the calculator. 3 times 9 plus 13, that'll give us 40 meters going this way. And the hypotenuse is going to be 3 times, plug in 9 again in this location, plus 14. You notice we just basically did that computation, just add 1, so that'll save us a little time on the calculator. And that will be 41 meters. So once we found X is 9, pretty much our job was done. We just came back here, substituted 3 more times. Well, that's a pretty fast substitution. And then did the computations on these two. Well, we've got the values. This was a lot of computation. So again, if you can find an easy check available to you, it's always well worth your time. But any questions at all getting to these 3 values, the 9 meters, 40 meters, 41 meters? Okay, let's do that check just because it's pretty fast. We have a right triangle. We have 3 lengths that we just found. So let's see if Pythagoras' theorem holds up with the lengths that we just computed. Take out the handy calculator. First, I'll do c squared and get a number. C is the length of the hypotenuse, so it would be 41 squared, so 1,681. Now the left-hand side is going to be a squared plus b squared. A squared is x squared, which is 9. So go 9 squared, then plus b squared. The value of b on this one was 40 meters, so plus 40, then square it, and it balances at exactly 1,681 on both. That tells us we have extremely good numerical evidence that these are indeed the correct side lengths. It'd be some kind of crazy mathematical coincidence to have values here that work in Pythagorean's theorem, but we made some mistakes and they're actually not the right one to solve the problem. Well, we did it, folks. That's probably the harder equation solving that we'll see in section 6.5, because there's just lots to put together when we went to and solved this equation. Well, I think we solved an equation like this way back in the day. I think week 1, maybe even day 1. Let's take a look at how that one went, just to compare their results. I think this was in section 2.3. This feels like a long time ago. We're just about closing out week 7. But on week 1, somewhere down on the line on these notes, here it is, we had a right triangle. We had, well, given lengths, A was 11, B was 60, and we had to solve for 61. Why was this one so much easier? Well, there was no variable x. We just had to plug in the information, crank it out, and then we took a square root. So that's why this one went really fast, but algebraic, well, by nature, it's really the same kind of problem. It was just more algebraically tricky once there was an unknown in the problem. We'll solve one more to close out the notes, and then we'll be moving over into chapter 7. So here's our next scenario for an applied problem. So Gianna is going to throw a ball from the top of a roof. Let me start over. Gianna is going to throw a ball from the top floor of her middle school. So let's hope Gianna doesn't hurt anybody. But when Gianna does that, when she throws a ball from 48 feet above the ground, the function, this one right here, models the height h of the ball as a function of time. This is kind of a weird expression, but all we're really saying is the height at time t becomes this quadratic. So let's throw that in there just for the notes to explain what the h of t expression is trying to say. It's not really a multiplication, it's just saying height at a certain time. So you can read the parentheses as saying height at. So this is read as height at time t. So the height at any time t is this altogether. So what would be the height at time 0? It would look like this. Height at time 0. We're plugging in a 0 for time here. That means we're plugging in a 0 here and a here, and we would just get 48. 0 plus 0 plus 48. So the height at time 0 is 48 meters, which makes sense because we were told in the information of the problem, when she throws the ball from 48 feet above the ground, that's what the model is going to be. So this is from the top floor, and this is from 48 feet above ground. So the instant the ball leaves this person's hand, it's 48 meters high. So that's the story so far. Well, what are we doing on this one? Is probably the big question. This right here models the height h of the ball as a function of time. So that's the h of t part. And here's the actual instructions on this problem. Find the time it takes the ball to hit the ground. So our whole objective is to do this. We're solving for time this time. But recall, h of t is the height of the ball. When it says hits the ground, this just means height is 0. But that's the height at any time t, this h of t object right here. So this is kind of a nice problem in a way. It's just kind of confusing because We're given a quadratic equation on the right. We're given something called a function, but all we're really doing is plugging in a 0 right here. So the very first step is go 0 equals negative 16t squared plus 32t plus 48. So that's our one and big step to solve the problem. And then from here, we're just going to be reusing the methods from before. It's a confusing one to start because of the new information, the fact we're dealing with a function. When it said to find the time it takes for the ball to hit the ground, we had to interpret that it meant the height was 0 and plug in that 0, or else it would be really hard to start this problem. It's nicer than the last problem because the last problem had equations that looked like this. They were really busy. We had to build our own equation and then try to get there. So this one's a little bit nicer in the sense that the equation is here. We just have to interpret what the instructions are saying to do to start it out. So now that we're at this stage, our next objective is to factor this thing. Looks like the least friendly factoring we've seen all day, but if this has a greatest common factor, we would definitely want to make that our first step in working with this. There's also 0 on one side, so there's really two things you could do. You could divide out the greatest common factor from both sides, or just factor it from here. Really, it's kind of up to your option on this one. Well, let's double check what the greatest common factor might be. It won't involve t because there's a t squared, a t, and no t here whatsoever. So maybe it's a 16. 16 does go into 32 twice. We would be possibly dividing by a negative 16 on this one. If there's a negative in front, that's definitely a good choice to take out the negative. And yeah, that looks nice. It goes in negative 2 times. And for the 48, divide by negative 16, and we would get a negative 3. So the greatest common factor on this one is 16, and we can just rewrite this as 0 equals. Let's take the negative version. It divides here, leaving a positive t squared. Divides here, leaving negative 2t. And by the calculator, 16 divides here. Negative 16 divides there, negative 3 times in particular. So that's our next equation to solve. Again, if you don't like that negative 16, you can just divide it out on both sides and it's just gone. Let's leave it here just to see what that would look like if you decide to go that route. We have 0 equals negative 16. Now we factor this equation. This one's going to split as a t times a t. The negative here says we'll try a plus and a minus. And 3 is a great number to work with. 3 is prime, so we could try, how about a negative 3, positive 1. That should do the trick, since t times negative 3 plus t times 1 would give us a negative 2t. So we've got the right factorization. Now the zero product property, it involves 3 factors this time. Either this is 0, but that's impossible because it's a constant, negative 16, or this is 0, or this is 0. So now this splits as t plus 1 equals 0, or on this one, t minus 3 equals 0. The first equation gives us a problem. If we solve this, we get t equals negative 1 seconds, since time, I believe, let's double check, 48 feet. It never actually said that. Well, let's assume it's seconds on this one. It seems like that'd be about right for this problem. And add 3 to both sides on here, and it would be t equals 3 seconds. Let's just put it here, just for the sake of clarity. Function of time t measured in seconds. Put that in red as a quick edit to the problem just to make it more clear. This definitely would not be in hours. That'd be weird gravity, for example. So that makes sense. But what doesn't make sense is the negative 1 seconds. Gian is not a time traveler, so the ball didn't hit the ground in the past, she's just about to throw it. So this one's out, it's just nonsensical. It'd be the 3 seconds. You can imagine a movie in your head, someone, I guess this person is in middle school, throws the ball from 48 feet height. She's on the top floor, so it takes a few moments for the ball to hit the ground. By this model that the physicists set up for us already, we're expecting 3 seconds before it possibly hits the ground. Hopefully it doesn't hit anybody. Well, we did it, folks. That's the polynomial equation solving in a nutshell, getting through these sections. For the next chapter, we're going to be looking into a topic called rational functions. And section 7.1 is kind of just a warm-up getting into that new content. Any last questions at all before we turn over to the next chapter? Okay, so let's take a look at what those new interesting problems are going to look like. Chapter 7 is going to be all about solving rational equations. But before we talk about solving rational equations, we also have to discuss what do we even mean about a rational expression in the very first place. So a rational expression you can think of as just a fraction. Rational just means ratio of one thing to another thing. But when we say rational expression, we usually are considering something like this, where p, it doesn't have to be just a number. It's allowed to be, but it could be a bona fide polynomial. And likewise, same for q. By polynomial, we mean things like 18x squared minus 4x cubed plus 2. This would be a degree 5 polynomial. The denominator down here is a quadratic because it's degree 2. So all the following below would be rational expressions. The only thing we're eliminating is the 0 polynomial. Q cannot be equal to 0 because division by 0 is, as always, undefined. But p could potentially be an ordinary integer. It could be a fraction, any real number whatsoever. So this one would be a rational function. The numerator just happens to be 89, and the denominator is quadratic. You could flip that around. The denominator could be a constant, 15. The numerator here is a polynomial, this one of degree 3 this time. And these are considered bona fide polynomials as well. The numerator and denominator could be just integers, like in this particular example. And even though it's weird, we usually would just call this a fraction. It's also considered to be a rational expression as well. These first 3 rational expressions are different than the one on the far right. That one is always constantly equal to 2/3. But the value of all 3 here, they depend on what value you pick for x. So this is what rational expressions look like, just fractions, now involving variables x like we've seen before. Something that's not rational would be something along these lines. Absolute value of x plus 5 over 3x squared. The problem here is the x plus 5 made it not rational when it's placed in an absolute value. So this one is not a rational expression. Likewise, something that's not rational could be 4x squared minus 7x. So far, so good, everything's fine. But it's no longer rational when we put in the cube root of 8 minus x. So we can't have expressions like these either, cube roots of things. This would make it non-rational at the same time. And when we said both p and q are polynomials, that means the exponents that we see here are integers, like 3, 4, 5, for example. So if it goes like this, 18x to the power of maybe 5 halves minus 4x cubed plus 2, 12x squared minus 8x plus 9. It's almost exactly the same one where the red dot is, but make that one change, put in power 5 halves, and it's no longer rational. So these are just the 3 examples of the things we don't consider rational expressions that we wouldn't be working with as our main objects in chapter 7. And this one down below is a bona fide rational expression. Like I mentioned, these things vary on the choices of x. So that's what we'll do for kind of a warm-up problem on example one. Well, any questions, folks, on what we mean by things that are rational versus what you might call irrational? Okay, when it says to evaluate the rational expression, all we're doing is placing a value in for x and cranking it out. So this is kind of a nice cognitive break, or this is really just following the order of operations. When x is 2, this whole expression, x squared minus 9, over x cubed minus 1, becomes something like this, the 2/3, but maybe a different value. Let's see what it comes out as. We'll get a 2 squared here, minus 9, over 2 cubed, minus 1 in the denominator. So up in the numerator, this is now 4 minus 9. In the denominator, this will be 8 minus 1. So this turns into -5 in the numerator, 7ths. So this rational expression becomes the fraction -5/7 at x equals 2. The concept here is change the value of x, and you're most likely going to change the value that the rational expression takes on. So plug in 3 here. When x equals 3, you'll get, this time, let me copy it in just to show the substitution. This is going to turn into 3 squared minus 9, divide by 3 cubed minus 1. But just like before, we can crank that out as well. In the numerator, we now have 9 minus 9. Denominator, it's 27 minus 1. So this becomes 0 over 26. And this number is okay. 26 goes into 0, exactly 0 many times. So the whole thing would evaluate to 0 this time. So when x is 3, the whole thing is literally the number 0. That's kind of interesting. And last, when x is 1. When x is 1, this rational expression, x squared minus 9, divide by x cubed minus 1, turns into, we plug a 1 here, so it's a 1 minus 9. Plug a 1 down here, this is just 1 minus 1. 1 to the power of 3 is still just a 1. But that means we now this time have a -8 divided by 0. And this is fundamentally different from before. This is undefined. Division by 0 is not allowed. And we got undefined not because this is undefined. This has meaning. There's nothing wrong with the rational expression. The problem was the number x equals 1. X equals 1 is something that we're on the lookout for. We're going to call this an excluded value. Because we got undefined when we plugged it in. It's undefined because of the 0 in the denominator. So that's going to be the next concept. Well, really the major concept in section 7.1. When are our rational expressions undefined? What are the excluded values? The reason for all this is what we really want to do in this chapter is solve equations involving these kinds of things, rational expressions. For example, we'd want to solve this equation. When is this true? The most important thing we have to keep in mind, though, is that would never be a solution to that equation, because when it's plugged in on the left-hand side, we get an excluded value. So building up a list of excluded values is just going to be the list of exceptions, the things that don't actually solve the equations. Well, that's our next topic. Any questions at the moment about this one here? Okay, so to put this excluded value idea down more firmly on paper, here's the definition. Excluded value, sometimes called a restricted value. Either way, it sounds like something bad. An excluded value of a rational expression is a value in the variable expression that makes the denominator equal to 0. That's kind of interesting in a way because the very last section was solving polynomial equations set equal to 0. So these concepts actually overlap in kind of a nice way. If we ever talk about the domain of a rational expression, the domain is all the good values. It's the values of the variable that are not excluded. So in this example too, really all we're going to go for is find the values for which the rational expression is undefined. We're looking for the excluded values, in other words. So the thought on every one of these is kind of fun in a certain sense. An excluded value makes the denominator equal to 0. So we immediately just go to the denominator, pick it out, whatever it is, set it to 0, and solve. This seems kind of weird because we're looking directly at what would make it an excluded value by ignoring the numerator. The numerator is just here to distract you. The excluded value is x equals -3. So that is the excluded value. And by the way, a pretty good shorthand for this would be E dot V dot for excluded value. We might use it here and there. It's a decent shorthand for the notes. So that's one down already. These go pretty fast occasionally, like in this case. There's just only one way to solve this equation because it's degree 1. This one is of higher degree. Doesn't mean there's 4 solutions, but it means there's at maximum 4 solutions to this one. It could be 1, 2, 3, or 4. We have to solve this to find out. But before we jump into, that's kind of numbered in a weird way, let's call this part B, just so it's a less of a distraction. I guess that's not exactly a number, that would be a letter. That'd be part C. Forgot my alphabet, I suppose, before writing these notes. This would be part D. And part E. Okay, sorry for the distraction there. Any questions on getting through this one? Okay, let's start this off again. We're looking for when this rational expression makes sense, when it's defined. In other words, we're trying to avoid this from ever happening. We want to find the numbers that set the denominator out to 0. And so we start by just picking out the entire denominator, not scribbling on it. Let me get the highlighter. Pick out the entire denominator, 25 x power 4 minus 30, x cubed, set it to 0, and solve. So this is what the mantra is going to be for every one of them. It's all about the denominator. We don't care if the numerator goes to 0. I mean, that happened here. The whole value is 0 in that case. So now solving this one, notice this is just another big review on factoring like we did at the start of the last section. There's a greatest common factor on this one. We can take out, looks like a 5x cubed. If we factor out a 5x to power 3, 5 divides 25, leaving a 5 here. X cubed into x power 4 leaves an x. 5 goes into 36 times. And then the x cubed would cancel out completely on this term right here. So we have 5x cubed times 5x minus 6 equals 0. In a certain sense, this is even easier than the last section because the definition of excluded value just means put in an equals 0 right here. So we never have to move things from one side to the next. The first step of solving this equation is already done. Then it's the matter of the zero product property. There are 2 things multiplying, resulting in 0. First one, 5x cubed equals 0, or 5x minus 6 equals 0. These are both solved pretty fast. The only thing that makes this true is if x was 0 itself. So there's one solution. And on this one, we can add 6 to both sides. 5x is positive 6. Divide by 5. X is 6/5. And these two are the excluded values. So really, this is kind of a nice section 7.1. Really, we're just solving polynomial equations again, looking at it from a different point of view. It's part of a larger problem. We're really wanting to look into rational functions, but it's nice to get an immediate review after discussing that section. Well, these go pretty quick sometimes, but other times they're kind of confusing. This is the first problem that I would say is extra tricky. We're looking for the excluded values on every one of these. So you take x squared plus 9. Let me try again. Take x squared, there we go, plus 9. Set it equal to 0 and solve. And now we have a problem here. You can see the problem emerging in two different kinds of ways. Recall from the last section, this is a sum of squares. That means immediately, once we recognize it, it's something squared, x, plus something else squared, 3. This is non-factorable. If it was this, x squared minus 9, we could work with that because that factors as a x plus 3, x minus 3 by the difference of squares formula. But not this one. This one's kind of broken in a certain sense, only because we're restricted to just ordinary real numbers. So we can't factor it. Already, this is telling us possibly something about the problem. You might try to do something, though. You might try to say subtract 9 from both sides. But the picture gets even worse. X squared equals negative 9. This has no real number solution at all. Because if you think of a solution, it's some number x. X times x is what x squared is. The law of signs say you can never get a negative. Either you picked a positive number and you squared it, that would come out as positive. Or if you picked a negative number for x, that negative number times itself is a negative times a negative, it's still positive. So this, no matter how you look at it, has no solution. And no, that's okay. It just tells us there are no excluded values. And that can definitely happen. That's what's going to happen on this one. So watch out for these. They could come up in the homework as well on the Newton homework system. Sometimes we're expecting to put in a number, but a valid answer some of the times is no excluded values whatsoever. This as a rational expression makes sense for every single choice of x. This one, you just can't put in 0 and 6/5, or else you've divided by 0 in both of those numbers. Well, I feel like that one's kind of tricky, but any questions on getting through part C? Okay, we just have a couple more that will close out the notes for the day. So last two, same idea, we're looking for excluded values. Really, this is just an opportunity to practice even more factorization at this point. Anytime you're looking for excluded values, you're wondering, how could this be undefined? Even though it looks abstract, it's just an ordinary fraction with a variable x inside. The only way it's undefined is if you divide it by 0. And you can divide by 0 the moment 4x squared minus 1 is itself equal to 0. So in every single one of these problems, we've always ignored the numerator. Negative 5 wasn't an excluded value on this one. Doesn't matter how simple the numerator gets or how convoluted it is. Sometimes you might notice the numerator factors in a readable way, but just ignore it. It's just there to distract you, basically. The denominator is all that matters for excluded values. And this one is a difference of squares. Let's cite the formula just for quick reference. This one factors by the difference of squares, which says a squared minus b squared always results in an a plus b times an a minus b. So we'll split up this in the same kind of way. To get a 4x squared, just multiply 2x times 2x. Signs of the middle are mixed, so plus and minus. And 1 is a perfect square because 1 is equal to 1 times 1. Now we're back to the zero product property. Take both of the factors, set them to 0, and solve. At this stage, it's a good idea to mention, if you just eyeballed it and noticed if this was set to equal to 0, x would be -1/2. That is an okay shortcut to take on that step. I think it makes the notes a little bit mysterious, and it could be sketchy on exams because you want to be more careful. So I'll always write in the step just to make the notes more readable. So this is 2x plus 1 equals 0, or 2x minus 1 equals 0. They're both solved in basically the same way. On the first equation, add 1, then divide by 2. Excuse me, let me try again. Subtract 1 from both sides, and then divide by 2. So x is going to be -1/2. Or, now this one add 1. 2x is equal to +1. X would be equals to 1/2 are the excluded values. It's a good idea to write this down, even if you just write the E dot V for excluded values on this, just as a reminder. These aren't the things we want. These are what we're going to try to avoid in the next sections when we're solving the equations involving these things. Well, that one was just a review of factoring a difference of squares as we see it in an equation like this one. This one is not too bad either. If you look at this one really carefully, this one appears to be a perfect square polynomial. The pattern for that is a squared plus 2ab plus b squared is a plus b squared. So same exact mantra. Take the denominator, set it to 0, and solve. V squared plus 10v plus 25 is now set to 0. But this is a perfect square polynomial. Potentially, looks like the 10v is going to make it work out. The thing that's a giveaway is the 25 there being a perfect square, 5 times 5. It strongly suggests put a 5 here and a 5 here to make up the 25. Then a v and v will make up the v squared when we FOIL. Signs have to both be positive. So it's v plus 5 times v plus 5 set equal to 0. This one's kind of different from all of the rest. I mentioned before, when you have degree 2, that means there's at most 2 solutions. This is the first time in the notes where that at most 2 solutions is accurate, because this is an exception. It has 1 this time. So degree 2 as a polynomial means you can't have more than 2, but you could have 1, and you could also have none, like in this case. So degree 2 means at most 2 solutions. This one you could rewrite as v plus 5 squared equals 0. But then we would just take the v plus 5 itself, set that to 0, and v would be -5. So this is the only excluded value. It's a unique one this time. So anything can happen if it's degree 2. There could be no excluded values, a unique excluded value. This happens only when it's a perfect square quadratic problem equation here. Or it could be 2 distinct excluded values. That's the more typical ones that we saw in the notes. Well, I ran out of problems. It doesn't go any below this, and I felt putting the notes for the next section is really too early. That'd be weird to try to start it right now. So we'll call it a day here a little bit early today, 6 minutes. Any questions at all before we call it a night? Okay, well, have a great weekend, folks. Early Friday morning, I'm going to be writing in that exam information. If you have any questions while you're studying, if you decide to study a little bit early, I'll be happy to help out. But otherwise, I'll see you all next Tuesday. We'll be in the next section. Thanks. Have a good one.